Now, you see something interesting around over here, and what you see something which is interesting around over here is that whatever you look as a partial graph ultimately has to be linearized. So whatever arrow weren't added, they could be done in parallel in any order, or in general, if I have something like a A1 and a A2, between start and finish, I could say start A1 A2 finish or start A2 A1 finish. If two nodes are in parallel without a edge specifying temporal constraints between them, they could be done in any order possible. So let's consider one such order, assuming this is the complete partial planning graph, which appears to be a complete partial planning graph. And let us write down one such linearization. So one such linearization will be start, then leave overnight, then remove spare comma trunk, and then put on. However, what this does is something interesting, and for now let me just highlight in for one variable what would happen. So when I apply the start action, I'll have add spare comma trunk. Oops. Okay, so I'll only chase what happens to this variable. Now I apply leave overnight. It has not at spare comma trunk. Good enough. So something which was positive at spare comma trunk has now suddenly become negative. Now I apply the third action, as I said, remove spare comma trunk. In any case, I cannot say put on because remove needs to be done before put on. So now I apply in the third action, which is of course my remove spare comma trunk, and this has its precondition as at spare comma trunk. Now the problem is that leave overnight undoes add spare comma trunk, which start was achieving for remove spare comma trunk. So these are extremely complicated things. So let's simplify by calling it as A1, A2 and A3. So my partial order planning was something like this, and this as P. So this was my partial order planning graph. A1 was achieving P for A2. A1 was achieving P for A2. A1 was achieving P for A2. And what happened, I added another A3 which has an effect as not P. And therefore, if I linearize it in this way, which is what I did over here, A1, A3, A2, A1, A3, A2. So A3 undoes the condition P for A2, giving you a third visualization of the same thing. So two diagrams and one text. So I say A1 achieves P P for A2 and A3 has effect not P, then we say, if this and this, then we say A3 is a threat to A1 achieves P for A2. So we say A1 is a threat for A1 achieves P for A2, and if A3 is a threat for A1 achieves P for A2, that means the linearization A1, A3, A2 is not possible. So we've looked at the text over here, A1, A3, A2 is not possible. We've looked at it in this small diagram here, A1, A3, A2 is not possible. And we've also had a look at here that A1, A3, A2 is not possible. So again saying, leave overnight produced not at spare comma trunk. Start was achieving at spare comma trunk for remove spare comma trunk. And hence A3 is a threat for A1 start achieving not at spare comma trunk for A2 remove spare comma trunk, or leave overnight is a threat to start achieving at spare comma trunk for leave overnight spare comma trunk remove spare comma trunk. And if that happens, A3 cannot be in the middle, and if A3 cannot be in the middle, that means there are two solutions to it. The first one is promotion. The second one is demotion. So if you need to promote, you say A1 achieves P for A2, then you promote A3. A3 cannot be middle, either it will be after A2 or it will be before A1. If it's after A2, it's promotion. And the other one is, of course, A1 achieves P for A2, you do it before. If you do it before, that is absolutely okay. So this example was pretty much complicated. Let us study it by another English language example very quickly. So I say that I have an action called as start AI notification. And if I say start AI notification, what happens is everybody quickly comes running to attend my class, and the effect of that is, of course, that sitting in front of system. And then what happens is that you are watching AI videos, and I do these actions in exactly the same format. First, I notify you, hey, starting time, then everybody comes and sits. So start AI notification achieves sitting in front of system for waiting for watching AI videos. Wonderful. And if you have an action which is you need to go to washroom, the effect of it is, as discussed, that you are not sitting in front of system. So if you need to go to a washroom, it is threat for start AI notification, achieving sitting in front of system for watching AI. And that's exactly what we say. There are two ways you can solve this problem. One is look at the videos, finish looking at it, then go to the washroom. Promotion. So this is what is promotion. I notify, you watch my videos, then you go to the washroom. Perfectly okay. The second one is that you know the timings, you know everything up. You first go to the washroom, Then I notify you about my start of class, and then you come, sit, and watch videos. That is demotion. So, even though this spare tire problem appeared to be solved completely, but there is something that I should be wary about, which is this is a threat. So this is a threat for this. That means I'll first try demotion and then I will try promotion. Let's try demotion first. That means it is leave overnight, start, remove. It has to be first this, and then this. So this is what I mean. This is already a link, so I add this link. This is not achieving anything. It's not associated to little. It's just saying that in order to break the threat, I add this temporal constraint. Now the problem is nothing can be before start. Absolutely nothing on earth can be before start. Start is the first thing to happen. This is said by saying, even though I do not draw it up, start is before every action AI and finish is after every action AI. This link and this link always exists. I do not draw it up because the graph would become absolutely clumsy. So nothing can get before start, and because nothing can go before start, I am at a trouble. My demotion strategy failed. And if my demotion strategy failed, I will try the promotion strategy, which is first let this achieve spare comma trunk for remove. So let's first have this, then let's have this, and then let us have in this, or I add in this as a temporal constraint. So, and that pretty much does seem to be solving in the kind of problem that I was looking at. Now there is another problem. So there is also not at spare comma ground. How do I know about it? Leave overnight, not at spare comma ground. Now why is not at spare comma ground important? Why did I suddenly get this variable out of all? Because remove spare comma trunk, it achieves at spare comma ground for put on spare comma axle. So because leave overnight produces not at spare comma trunk, so not at spare comma trunk is a variable p, and beyond this variable p, leave overnight is also a threat to this pair. That means leave overnight before this cannot happen. That means this needs to be happen before it, which cannot happen because it will violate this constraint which I have already added and I am committed to it. Or I'll have to go after this, which is also weird. So let's discuss promotion and demotion. Just to let you know the new nomenclature, my new nomenclature is, this is A1, this is A2, this is P, and this is the threat A3, and this is already confirmed, so I'll take it as a confirmed link. So now I try to remove this A3 being a conflict to A1 achieves P for A2. So first I try demotion. That means in demotion this has to be 1, this has to be 2, this has to be 3, this 2, 3 is in order, this has to be before this, or I add this. A partial order planning graph cannot have cycle. The moment there's a cycle, there is no topological sorting that you can do. It has to be acyclic. So bad idea. So let's try promotion then. So let's try promotion. In promotion, this has to be 1, this has to be 2, and this has to be 3. So 1, 2 is already in place. So let us add this here. And again, there's a problem. So you do end up in a cycle. Neither promotion is possible nor demotion is possible. That means this problem is non-solvable. So after doing all this, I do get that there is no solution which is possible. And because I get that there is no solution which is possible, of course, I will have to look at some other children. So there are actually two ways to satisfy. Now I'll come to the actual solution at flat comma axle. Now let's see if there is another not at flat comma axle. So there would have been two children. One of them would be leave overnight. That failed. So do I have another way of satisfying not at flat comma axle? Not at flat comma axle. Yeah, there's another one. So that's basically what is... Oh, that's a precondition. I cannot be counting on precondition. Is there another not at flat comma axle? So yeah, there is not at flat comma axle for object is equal to flat and location is equal to axle. So I think I add that one over here. So the action is called as remove flat comma axle. And just to say, I mean, of course, I know that there won't be any more threads. So not at flat comma axle, not at flat comma axle, that's okay. At flat comma ground. I cannot write it directly here just to say that there is another action which is possible. So at flat comma ground. That's not the thread. You can just verify it now. That's not the thread. Does it have preconditions? I think it has at object comma location. So object is flat, location is axle, and luckily that is already satisfied. So the partial order planning graph is what is complete. And it does occur to me, I have written everything but the name of the topic. So let me write it down over here. It's called as the partial order planning. Let's summarize this up first. So what did I do is something very simple. So each one of the vertices in my forward search will be a partial graph, and then I'll look at all the flaws, I'll look at all the unmet condition, I'll look at one of them, I'll select one of them, and I'll say that, okay, can I have an action which has that as an effect, and I eliminate that flaw. In doing that, I will generate more flaws, but I'll take care about them later. And I stop when all the flaws that I have are already satisfied by the source. And it was a very simple algorithm. Heuristic is also simple. So you have to minimize flaws. That means out of all the actions possible which meet a flaw, you need to select the one which increases the least number of flaws, which has the least number of new flaws added, or which has the least number of preconditions, neglecting the ones which are already open somewhere else. So that was simple. However, the problem came out to be when threats happened. A1 is achieving P for A2 and A3 is a threat. Now you need to add links such that you either demote it or you promote it. Sometimes both would be possible. Sometimes neither would be possible. If neither is possible, then you try some other action, undo some of your previous moves and select in something which is new. Now the interesting thing about AI is when searches started, they were honestly impractical to solve any real life problem. And then this wonderful thing happened called as heuristics, and suddenly everybody's like, okay, now we can solve problems which were unsolvable and achieve great results. Then what happened? This classic planning things came out, and with all the propositional literals, the backward search, the forward search were unsolvable problem, even with heuristics. So they could achieve some success, but we did not have great heuristic to solve them up. So it became a gloomy note. You've got exponential complexity, the heuristics are not doing good, practically things are not solvable. Of course, at the other end, compute and the requirement increase, so machines had to be excessively sophisticated, and then the partial order planning comes. So what it does is effectively it reduces your depth, and that has a great value by saying that I can have parallel architectures, I can have parallel structures, sub-goal independence. People realize it has three sub-goals, all of them are independent. So at each level you could parallelly compute things up. Goal is ABC, all three of them independent of each other. In parallel you could achieve ABC. In achieving A you will open A1, A2, A3, which can also be achieved in parallel. So this great news comes in, partial order planning, and then it's made unsolvable problems solvable. However, then people realize what new thing that come up, constraint satisfaction problem. Does the same thing, excellent heuristics, and it could virtually solve anything. As long as it was constraint satisfaction problem, graph plan, essentially it became constraint satisfaction problem, and that is where the graph plan started to take a lead out of partial order planning. So when I started teaching, I used to spend a whole lot of time teaching partial order planning. Look at it now. I'm more a fan of graph plan as compared to the traditional partial order planning, or to say that the days of partial order planning are not really there now, because constraint satisfaction problems used in the planning graph have reached into that kind of a sophistication